All right, guys. So in 6.4, what we're going to be talking about, we're going to do a little bit of review talking about the nearest neighbor that we talked about in 6.3. And then we're also going to look at a very closely related algorithm, which is the repetitive nearest neighbor algorithm as well. So just as a reminder for the nearest neighbor algorithm, here's what you do. Basically 2 steps. The start is that you start at the designated vertex. If there is no designated starting vertex, then you just pick any vertex you'd like. And then from that starting vertex, you go to its nearest neighbor, i.e. the vertex for which the corresponding edge has the smallest weight, meaning the cheapest, the smallest amount of time, so on. And then from every vertex, you then go to its nearest neighbor. So from the ones you visited, you only now choose among the vertices that have not yet been visited. And you just keep doing this until all the vertices have been used. And then from that very last vertex you end up at, you return back to the starting vertex, and you're done. So, as you might kind of pick up from the name, repetitive nearest neighbor is going to be a variation of the nearest neighbor algorithm, but we're going to repeat the process a few times in order to try to find an even better route. So why would we do this? The nearest neighbor tutor, it all depends on your choice of starting vertex, but if we change that starting vertex, then we might get some different results and might even do a little bit better. Now, since finding a nearest neighbor tour is efficient, then it's pretty reasonable to repeat that process several times then. Obviously, if it was brute force algorithm, we wouldn't want to repeat that multiple times. But in the previous video, if you remember, nearest neighbor doesn't take very long. So we can actually do it multiple times and still be a fairly efficient process. Now, here's the drawback, is if you think about what we're going to be doing, repetitive nearest neighbor is we're going to be picking different vertices to start at, but that's really not what we're supposed to do. We're supposed to start and end at a single vertex. But it's actually not going to be a problem. In fact, once we've got a circuit, we can actually rewrite that circuit in order to make sure that it has the correct vertex as its starting point. So let's go back and think about the 2 or 5 cities. We'll continue to use this example 6.1, in order to kind of look at these different algorithms. So just a reminder for nearest neighbor, what we ended up with was ACEDBA. So ACEDBA, and that was again looking at the weights with that. A to C, C to E would have been, let's see, this one right here, E to D, D to B, and B to A. And if you recall, I believe that cost us around $773. So that was a total cost of $773. Now, here is kind of the next thing that we're going to do is now let's talk about the repetitive nearest neighbor idea. So instead of starting at A, let's start at B and do this a little bit differently. So if we use B as our starting vertex, let's kind of see how this would work. So starting at B, looking for our nearest neighbor, looking for the cheapest possible route. And we've got 150, 121, 200, 285. 121 is obviously cheapest, so that takes care of B and C. Next, from C, we're looking for our cheapest. So A is 119, E is 120, D is 174. Pretty clearly, A is going to be cheapest, so we're going to go ahead and choose that next. From A, we need to go to either E or D. E is 133, D is 152, so 133 is cheapest. We're going to go to E. And now we only have one choice, which is to go to D, which for 199. And now from D, remember we started at B, so we're going to use 150 to go back. So it looks like our tour, if we were to write that out, would be that we went from B to C, C to A to E, E to D, and then D back around to B. And let's see how much this tour costs. So 121 plus 119 plus 133 plus 199 plus 150 is going to add up to be a total cost of $722, which is great. In fact, that's much less than what it was for just our nearest neighbor. In fact, it's like $51 less. But it doesn't start at A. And so here's what we're going to do. We're gonna actually make it start at A, and then we're going to kind of use this same circuit, but starting at A instead. So from A we went to E, from E we went to D, from D we went to B, from B we went back to C, and then from C we went to A. And if you look at what that would cost, A to E would be right here, E to D right here, D to B right here, B to C right here, and C to A right here. It actually costs the exact same amount. It is actually the exact same circuit. So when you look at circuits, circuits are actually kind of multiple circuits in one. It doesn't really matter where you start at. So that's why repetitive nearest neighbor is going to end up working the way it does. And you can see that in this slide. They kind of talk you through it again. So if you want to read that later, you're more than welcome to. So let's say we continue to repeat this process for our other vertices, C, D, and E. And I'll work through these with you so you can see kind of how they work. Let's go ahead and start with C. So for C, our cheapest vertex would be to go to A for 119. From A, our cheapest would be to go to E. So far that's C, A, E. Then let's see, from E, we can go to D for 199. From D, we have to go to B. That is 150. And then from B, we go to A, which is, or from B, we actually go to C. Let me get that fixed, because remember, we started at C. So from B, we go back to C, which is 121. All right, so let's determine the cost there. So that would be 133. Well, let's start with the 119. So 119 plus 133 plus 199 plus 150 plus 121 is going to be a cost of $722. In fact, I believe that is the exact same circuit as we found before up here. So even though we're starting at C, that would still be our cheapest. And so our repetitive nearest neighbor actually ends up being the same. Now let's go ahead and do another one. This time we're going to start at D. I'm going to switch colors here to kind of help us distinguish between them. So looking at D and looking for our cheapest possible route, it looks like $150 to B is going to be our cheapest. From B, let's see, we can go to C or A or E. And I think the cheapest there is going to be to go to C for that 121. From C, we can go to A or E. It is just a little bit cheaper to go to A. And then from A, we can go to E. And now we've covered all of our vertices, so time to get back to D. And then we'll be done. All right, so let's go ahead and calculate the cost. So from D to B, that's 150. B to C is 121. C to A, 119. A to E, 133. And E to D, 199. Gives us a total cost, once again, of $722. In fact, once again, that actually was the exact same circuit. It just depends on how you want to start it. All right, one last one to try. Let's see if starting at E we can come up with anything different, anything maybe a little bit cheaper. So from E, looking at all of our options, 120 is our cheapest. That would be going E to C. From C, we can go to D or B or A. Cheapest there is going to be to go to A. Now from A, we can go to either D or B. It's going to be cheapest to go to D. So then from D, we have to go to B. And from B, we're ready to go back to where we started. So from B, we're going to go back to E. All right, so let's go ahead and calculate this cost, see what we come up with. So from E to C, that's 120. C to A, 119. A to D, 152, D to B, 150, and B to E, 200. And this one actually is different from the previous circuits. It actually ends up being a little bit more expensive, actually, 741. All right. So, and again, they give you kind of a summary of that in this slide. And so if you need to go back and look at it, obviously you can see what they came up with was the same as what we did. So it looks like we have some different costs now that we can compare for nearest neighbor. And in fact, out of all of the nearest neighbors, the cheapest one was a cost of $722. In fact, we found that 3 out of the 5 circuits for repetitive nearest neighbor were $722. And so, yeah, that ends up being the cheapest. The other two, I believe, were $741, and the original nearest neighbor, which was $773. So we're going to pick our cheapest, which, even though there were 3 different circuits, really, they were the same. It just means that you needed to start them all at A, and then they all, in fact, end up being the same. So that's repetitive nearest neighbor, is you basically pick a different starting vertex each time, and then just do nearest neighbor for each of those vertices, rewriting them to start at whatever you need to when you are done. So here's the algorithm for that. Here's your step-by-step so that you can write these down. Again, I would very highly recommend anywhere it gives you these step-by-steps for these. So going back up to nearest neighbor, it gave us a step-by-step here. This would be some good stuff to have you copy down in your notes. And now we are ready to copy down the steps for repetitive nearest neighbor. These will also be some good things to copy down in your notes. So let's let X be any vertex. We're going to find the nearest neighbor tour starting with X and calculate the cost of that tour. We're then going to repeat that process with each of the other vertices on the graph as the starting vertex. Once we've done that, looking at all of our nearest neighbor tours, we're going to choose the one with the least cost. And if necessary, we'll rewrite the tour so that it starts at the designated starting vertex, and we'll call this tour the repetitive nearest neighbor tour. Now, in comparison to our previous tour, remember nearest neighbor tour, we looked at what was called a relative error. We were able to calculate that the relative error for nearest neighbor was 14.35%. Let's go ahead and do the same for repetitive nearest neighbor to compare to see which one is maybe more efficient. So remember, for our repetitive nearest neighbor, $722 is what we came up with for our cost. So to find our relative error, we're going to take that minus the optimal route, which remember we found using brute force method in the previous video, and then divide by that optimal tour. So 722 minus 676 is going to be 46, so you were off by quite a bit less. Remember, nearest neighbor, you were off by 97. Repetitive nearest neighbor, we're only off by 46. And when we divide that by 676, our relative error is now just 6.80% for our relative error. So now we're only off by a little under 7% instead of being off by as much as 14%. So you could almost say that repetitive nearest neighbor is twice as effective as the nearest neighbor, at least for this particular example that we are looking at. In fact, in general, repetitive nearest neighbor will be better than nearest neighbor unless the nearest neighbor just happens to be the best route. Then it might just be that they are equal to each other. But in general, repetitive nearest neighbor will be slightly better than nearest neighbor. Alright guys, so that wraps up repetitive nearest neighbor. We've now seen 3 algorithms, which are brute force, nearest neighbor, and repetitive nearest neighbor, and you can probably start to see some of the advantages and disadvantages of those 3 methods. That being said, in the next video, we will take a look at our very last method, which is going to be the cheapest link algorithm. Until then, have a great rest of your day.